All right, everybody. It sounds like everyone's having fun with the warm weather, and I've discovered my hidden ability to power Alexa anywhere in people's homes. So that's actually kind of funny. Moving on in life, I don't have any announcements really, except that we're done the presentation. So that is great. I will be getting the grades from the TAs. If you have yet to submit your grades, to your TA, do so. They are effectively late, but right now, so they need to be in so that we can get all the grades up. Given the amount of material we've got, I will be teaching on Monday. I had hoped I could not do that, but it's going to happen. You got a lot. It's lots of examples to do. Your final exam is on the 24th, which is a Saturday in the afternoon, 1:30 to 4:30. I sent an email about that. So when will we get the grades? As soon as I get them and can analyze it. It'll only take me half a day to do what I need to do to them, but I need them from the TAs. So, and the TAs need it from the students. So when I sent a reminder to the TAs yesterday, I got 2 emails back this morning saying they're still waiting for, one person's waiting for 2 students, one person's waiting for 3. So, and I basically said, by the end of today, just hand them to me and I'll deal with those students or not. So, okay. And your marks from OChem had better be on Blackboard. So, and you should have gotten your marked organic worksheet back. Not with the correct answers, or the thing is already, the answer key is online. So, okay. I think I got this intermittent reset thing fixed. I'm going to hope I've got it fixed with different drivers, and we're just going to continue on. So yes, if you haven't got your OChem thing yet, I haven't actually checked to see what grades are in, email your TA, because I've emailed them. There is where we want to go. So last day we were looking at this. We made a connection between thermodynamics and electrochemistry with this equation presented here. Delta G is equal to minus the number of electrons transferred times Faraday's constant times the cell potential. In addition, we were able to derive the Nernst equation, and what's presented here is the Nernst equation under any temperature, and it is ultimately allowing us to calculate the cell potential when we're not under standard conditions. And it also is a link between electrochemistry and equilibria. The last thing we did last day is this example here. And it was a little bit rushed at the end because I wanted to get it done. Does anyone have any questions on this example? All right. So all right, I just shouldn't read the chat. What we want to do now is to drive another expression relating electrochemistry to a system that is at equilibrium. And that is what we are going to do right now. And then we're going to start using that. So with luck, we're not going to see any problems with cell potentials, or with cell potentials, with resetting, I hope. We have the Nernst equation. When we are at equilibrium, 2 things are true. One of them, what are those 2 things that are true at equilibrium? K is equal to Q, yes. And delta G is equal to E cell. That's all, not quite, is and 0. That's what I wanted to see, right. So at equilibrium, Q is equal to K, and E cell is equal to 0. There is no way of drawing energy out of a system that is at equilibrium. So when we substitute that into that equation, we are left with 0 is equal to or more commonly, and what this shows us is that there is a direct relationship between the cell potential and the equilibrium constant. Oops, sorry. So at equilibrium, delta G is equal to E cell is equal to 0, and we get that expression right there. So let's apply that. Let's determine the solubility product equilibrium constant for, which is otherwise KSP, for silver chromate as presented there. And we are going to compare it to the literature value. So what we need to do in this context is look for electrochemical data that deals with silver chromate. The equilibrium that we're interested in oops, this is an equilibrium. Is right there. So if we assign oxidation states to things, the silver ions are +1, the chromate ion is -2, it's a conserved entity, it's on both sides, -2, and that makes the silver ions +1. But we don't have redox. This is not a redox reaction. Are we able to determine a cell potential for a system that is not redox? Is there a voltage associated with a chemical reaction like this or an equilibrium like this? It's kind of a guess, yes or no? And we got people going no, and we got people going yes. We have this relationship right here. And in that relationship, what we have is a relationship between the cell potential and equilibrium constant. Nothing in there says, well, we have the number of electrons being transferred, but there's nothing in there that qualifies which equilibrium constant we're looking at. So the answer probably is yes. Well, I know the answer, but what do we need to do? Let's go back and look, and I'm not going to look, but if you look on the data sheet, you will find reactions involving silver chromate. And one of the reactions you're going to find is that of Ag2. So you're literally hunting for redox reactions. Goes to and we get that, and we find that there's a reduction potential of 0.446 volts. And if you call up the data sheet, it'll be right there at 0.446 volts. There's another redox reaction that is very common, seen, used regularly, and that is the reaction of Ag solid plus, plus reacts to give Ag plus an electron. And the reduction potential here is 0.8 volts. We can multiply the second one through by 2. And what we have happening is that the electrons are going to cancel, but so is the silver ions. The net result of all of this is we have the reaction and if you calculate the cell potential, realizing that the first one is a gain of electrons reduction, second one's loss of electrons oxidation, the cell potential here is negative 0.354 volts.
Roy, would you multiply the cell potential by 2 because you multiplied the whole equation by 2?
Why would I do that? Because we did it in thermodynamics, yes. But this property right here is an intensive property. We wouldn't multiply the voltage through by 2. What gets multiplied through by 2 is the number of electrons that are transferred. So the voltage is constant, but the current, the amount of electrons transferred, increases as a function of stoichiometric coefficient. So it doesn't matter if I have one molecule reacting, 1 mole of molecules reacting, or a huge, an infinite reservoir, it's all going to happen at 0.8 volts. Good. What has happened is that the entity up here, the entity being reduced, silver in the first reaction, and the entity being oxidized, silver in the second reaction, is the same entity. Therefore, it cancels out. So even though this is not redox, there is a cell potential associated with that reaction. And I can now take that cell potential and plug it into this equation here. Which is the same reaction, just at 298 Kelvin, log K. If you do the number of electrons being transferred, if we go back and look at the half reactions, is 2. And we can find out that log K is negative 11.97. And K is 1.08 times 10 to the minus 12. And if we look at the equation, moles per liter cubed. And this value is only known to one significant digit. Does that make sense? Or does anyone, what questions do people have on that calculation? And if we actually, where did I get the 0.05916 from? Let me just back up. When we did this example here, and I don't actually have it anymore, I removed my the pages that was doing this. When we did that example right here, and we calculated 2.303 RT over N electrons F, this became 0.05916 volts over the number of electrons at 298 Kelvin. Yes. Yep, the data sheet is that two-page, these values are off of that two-page data sheet. So all of these numbers come off of that two-page data sheet. Yep. Good deal. So when we compare our values to the literature value of 1.1 times 10 minus 12 to the value of significant digits, we're actually at 1.08, but we're limited to one significant digit. And so we can say that our value is consistent with the value in the literature. This puts into notes what we just talked about. There exists a free energy for every reaction, redox, and non-reaction. We can calculate delta G for any reaction. Is there a cell potential for that reaction? And we saw in the last example is that, yes, it just so happens that some of the entities cancel out. So the entity being oxidized and reduced happens to be the same, and it cancels out. Here's another example. So we're looking at the reaction. This is the autoionization of water. We have Kw, which we've calculated previously with using delta G. We're now going to look at it from an electrochemical perspective. We want to determine the standard cell potential using half reactions and the standard cell potential from the equilibrium constant. Haley, to answer your question, I will try, but I will try to make sure that you only use the data sheet. If not, I'll tell you on the question. But that's the goal, because the exams, when in a real exam environment, you would only have that data sheet. So the overall reaction that we're interested here is that of water is in equilibrium with H plus O H minus. We know that Kw, what was that, 1.0 times 10 to the minus 14 moles per liter. The trick is, again, to find reduction reactions that add up to that. And if you look at the data sheet, we have, for example, the basic reaction of water, and this is just a matter of searching for it or knowing the voltage. You can find that 2 waters reacts to give H2 gas plus 2 hydroxide ions. And the reduction potential for that is negative 0.828 volts. The other reaction would need to get rid of the hydrogen, and if we take hydrogen and react to give it 2H plus 2 electrons, this is the defined reaction that we use to set up all of the cell potentials, reduction potentials, and that's 0 volts. Electrons cancel, hydrogen cancels, and we are left with the reaction. Oh, sorry, there's a 2 in front of here, 2H2O. We are left with the reaction of 2 water reacts to give 2H plus 2 OH minus. gain of electrons reduction, loss of electrons oxidation. The cell potential here is negative 0.828 volts. 0. It says 0. But this actually, just pointing out, this actually isn't the reaction I'm interested in. I'm actually interested in that reaction, or half that reaction. And taking half that reaction, we have H2O reacts to give H plus O, H minus. This one is a 2-electron process. This is a 1-electron process. What is the cell potential for this reaction? Anyone? Kenzie and Haley say it's the same. Are they right? They're right. Yes. The cell potential is still 0.828 volts. That was part 1. Part 2 was to calculate the cell potential, or part B, cell potential from the equilibrium constant. So the equilibrium constant is, or the equation, and we're working at 298 Kelvin, so again, I could use either one. I'm going to use 0.05916. And here, for the reaction I'm interested in, number of electrons is 1, and the equilibrium constant for this is, of course, 1 times 10 to the minus 14. And plug it into your calculators and give me a value. But that's the number we got up above, Brianna. We got negative 0.828 volts there. Is it a surprise that we get negative 0.828 volts here as well? Given how good some of you on your calculators are on your calculators, sometimes it is a surprise. Ooh, was that hurt? Oh, sorry about that. I'm bad too, okay? I make stupid errors on my calculator, and you will all catch me. You sit there and go, but I got a different number, and I'm like, yeah, that's just whatever. So that's why I use Excel for data analysis. I plug the formula in, I make the formula work, and then it does it for every single one. Good deal. Yes, we get the same bullet value. So we can now make the connection between electrochemistry and thermodynamics and equilibria. And that is the relationship shown here. We have mathematical relationships between the free energy, delta G, the equilibrium constant, K, and the standard cell potential, E naught cell. And those mathematical relationships are presented there. This is all, if one wants to consider it. We taught equilibria different, then we taught thermodynamics, then we're teaching electrochemistry, but it is all linked through this mathematical triangle that you see here. So that explains the mathematical relationships we have. What we're going to be doing now is going into looking at specific applications: voltaic cells, electrolytic cells, concentration cells. So we're going to start that. Voltaic cells produce electricity spontaneously. Okay, batteries is an example, corrosion is an example. The demo I'm going to do in a few minutes is an example. Okay, batteries, which is the one that everyone uses on a regular basis. They're using now in your cell phones, in your watches, in your laptops, in your automobiles. They store chemical energy for release. Batteries are ultimately non-equilibrium systems because if they were at equilibrium, the battery would be dead. It would have discharged completely. So there is a voltage ready to be discharged, and all we're missing, if we go way back to the cell diagram, second, I'm going to actually put the cell diagram in there. If we go way back to that cell diagram, all we're missing is the wire connecting the two half cells. Corrosion is a voltaic process we ultimately don't want to occur. Oxidation, rusting of vehicles. In Prince George, when I moved here, I discovered that they don't put salt on the roads, which is awesome. Because if you live in Vancouver, Toronto, Edmonton, pretty much any major city where they've forgotten how to drive, you're going to find that there's tons of salt on the road. And I was back east a couple of years ago, and I could not believe that the roads were white with salt well, it would have been about March or April, as the snow had melted and the roads were dry, but they were white with salt. And that salt facilitates rusting of vehicles. We have three general classes of battery. The first class is that of a primary cell, which produces electricity from chemical reactions that cannot be reversed. It's not rechargeable. Secondary cells produce electricity from chemical reactions that can be reversed by putting electricity into the cell. They're rechargeable. These definitions are old, and they came from a time when rechargeable batteries were novel and unique and different. Now rechargeable batteries are everywhere. And alkaline batteries, you still can buy them for remote controls and the like, but there's an equal amount of primary and secondary cells in the world. Nickel metal hydride, lithium ion, lead acid batteries for automobiles are all secondary cells. And the third one is fuel cell, but it's not really a battery. It produces energy no matter what. As long as the reagents are present, a reaction will occur. The trick is to control the reaction such that only the correct amount of reagents come into contact, such that all of the available energy is used as electricity. If there's an excess amount of reagents, that will be converted not into electricity, but into heat. So hydrogen fuel cells, zinc air fuel cells. Zinc air fuel cells, no, not in watches. The example is on watches. Zinc air fuel cells are commonly in really small button batteries for things like hearing aids and the like. And I actually have a cute story with regards to zinc air fuel cells from when I was younger and more naive than I am now. Back in the good old days, talk to your parents, grandparents, I don't know how old I am. Back in the good old days, you actually replaced the battery in your watch. Now it's a rechargeable battery and you don't even have to take it out of the thing, but you replace the battery, and batteries were expensive. They were like $6, $8, and that was a long time ago, and that was really expensive. And so I actually found a package of zinc air batteries, a package of 6, and they said they were for hearing aids. And so I put them in my, but they were the same size as for my watch. And so I bought the package and I put them in my watch because I think the entire pack was like $10. And 2-3 months later, my watch dies. And I'm like, oh, weird. Well, cheap battery, put in another one. 2-3 months later, my watch died again. And by this time, I'm beginning to think that there's something wrong. So did a third battery. And at the end of it, the couple months later, my watch died, so I realized, yeah, it's not the batteries, it's the watch, and so I discarded the watch and threw it. Yeah, got a new one. It wasn't until many years later that I was in university, college, whatever, and I learned about fuel cells, and I learned about zinc air fuel cells, and I went, wait a minute. I went back to Astor, I didn't know it at the time, and I looked for hearing aid batteries, and sure enough, they were zinc air fuel cells that were designed to last 3 months. Why 3 months? Because there was stuff going on. 3 months because that is how long people who had hearing aids thought the battery should last. You could put more zinc in there and it would last longer, but people who have hearing aids, they're told the batteries last about 3 months. They last 3 months and away you go. So my watch was actually fine. It was the fact that I had bought fuel cells that were producing more electricity than my watch needed, and well, producing enough electricity for my watch, and the rest was being dissipated as heat. The things you learn after the fact. At least I learned. Okay. The nice thing about batteries and fuel cells is that the chemical reactions are fairly easy. Presented here, cell potentials for, oh, there's something on the chat, and I don't know what this is going on. Oh, not, whatever. I'll leave the chat. I'm not paying attention to that. You've all figured out that you can be in PowerPoint and not see the chat, so that's where I'm at. I have to advance the slides, so. Zinc carbon, zinc chloride, those are the historic old batteries from way. Alkaline batteries present is there. Mercury oxide, yada yada. Lead acid battery, we saw that already, and when we did an example using a car battery the other day. Nickel, cadmium, nickel zinc, nickel metal hydride, uses M, which is a metal, and it can be any one of the ones that's down below. And we get the different voltages there. Zinc air, iron air, aluminum air, methanol air. Of course, the oxygen in air is the reactant that is used in those fuel cells, and they draw in air to do that, to react it with whatever in a controlled environment such that you can get electricity out. So just a series of reactions that can be used for primary cells, secondary cells, and fuel cells. Because lithium-ion batteries are ubiquitous, let's just spend a little bit of time looking at what's happening here. The reaction is, on the left-hand side, you have lithium ions trapped in a graphite matrix. So those lithium ions are trapped in graphite hexane, that's well, benzene sheets, graphene sheets on the left-hand side. And so the discharge is to dissipate those lithium ions into that cobalt oxide complex on the right-hand side. In the middle is a salt bridge that only allows lithium ions to cross it. Nothing else can go across that salt bridge. And so when you're discharging it, the lithium ions are moving from the graphite, that would be anode, and they're moving over to the positive cobalt oxide cathode. To charge it, you just simply have to put electricity in the other direction, and more than 3 volts, right? You're going to get 3 volts out of this reaction. In order to charge this up, you have to put in more than 3 volts to drive the reaction in the other direction. So typically you're putting in 4 or 5 volts to cause the reaction to go, which is why a USB connection can actually charge a lithium-ion battery, because it's putting out 5 volts, and which overcomes the 3 volts that you see here. And the picture on the right-hand side is actually how it is laid out. The anode in separator, which would be the salt bridge, acts as a salt bridge, and the cathode are wrapped in a big long cylinder, like you see here, and that gives you more surface area, more current carrying capacity, so you can have a larger amp hours on the battery. If you have a cell phone battery, that is those nice little flat things, these things are just stacked on top of each other rather than put into a circle, but it is layered like a pancake. And highly recommend you never take one of those things apart because they react spontaneously with air, often explosively, but definitely with flame. So don't take apart a lithium-ion battery. Not good. You have potholes. Oh no, Wilhelmina, just reading the chat. There's potholes in Edmonton that swallow, well, almost swallow. They swallow tires for sure. I've seen 3 vehicles now where literally the car is damaged because the pothole is deeper than the tire. It's bad. Fuel cells. And this is how they generate electricity. Fuel cells are between 40 to 80% efficient. And we'll compare that to an internal combustion engine, which is at maximum about 35% efficient in everyday practice, between 25 and 30. And as I mentioned previously, if there are excess reagents present, it's going to release the energy as heat. We're going to start this reaction right now, this example, and then we're probably going to have to finish it next day because there is a demo that I want to do with regards to voltaic cells. So let's go through and look at this methanol fuel cell, and we want to determine the standard cell potential at 338 Kelvin. Want to point out something, we're not at 298 Kelvin. So none of the data that we have for cell potentials or reduction potentials is valid. It's only valid at 298 Kelvin. This is reacting at 338 Kelvin, so we have to go about finding that a different way. So the reaction that we're looking at is that of methanol, aqueous, the CO2 is actually aqueous too, it's not gaseous, and that's important to ensure the states of matter are correct. So this is a little bit different in terms of methanol is not a liquid, it's not a gas, and CO2 is dissolved CO2. In order to calculate the cell potential, we need to use thermodynamic data, formation enthalpies, and entropies. And I'm just going to give you the values. Anything for aqueous has to come off that large data table that's posted to Blackboard. And so those are the values, comes off of those data tables. And you can calculate the enthalpy of reaction and the entropy of reaction. The enthalpy of reaction is negative 739.5 kilojoules, and the entropy of reaction is negative 183.4 joules per Kelvin. So now that we have the thermodynamic data, enthalpy and entropy of reaction, which is generally temperature independent, we can actually calculate delta G, which is temperature dependent. Oops. And so delta G, 338 Kelvin, is negative 677.5 kilojoules. In order to calculate the standard cell potential, it's minus number of electrons, Faraday's constant. Sorry, let me back that up. E cell, or sorry, delta G is what I meant. Delta G is equal to minus number of electrons, Faraday's constant, E cell. We need to know the number of electrons that are being transferred. We didn't actually have to balance this thing via half reactions, but we can go up and assign oxidation states, and from that hopefully get the number of electrons being transferred. So just assign oxidation states 0 to that oxygen, -2 and +4 on CO2, -2 and +1 on water. For methanol, it's +1, +1, -2. And if you work that out, -2, -4, +4, -2, this needs to be -2 on the carbon. So if you follow carbon going from -2 to +4, that's a 6-electron process. You could follow oxygen going from 0 to -2, but because there are 3 of them, that is also a 6-electron process. So both of those things will show that you've got 6 electrons being transferred. If you need to write it out and balance it via half reactions to figure the number of electrons, that's fine. I'm just showing that you can get it from the assigned oxidation states. So number of electrons is equal to 6. And so we're able to calculate E cell and when you do that, you get 1.170 volts. That is the standard cell potential. Just give me a second here. That's really weird. It should be coming through. Okay, well, we're going to do it the old-fashioned way. Control 1, Control 5. Nope. Control 4. For whatever reason, I don't have the ability to talk to my camera, so we're just going to move everything around. Now I get to see myself too. And I'll move stuff over to the bench and see what's going on here. You need some safety equipment. I don't need my camera. So what we have is a couple of flasks. Actually, better idea. we go. Much better idea. Yay, safety glasses. Good deal. We have a number of reagents that are sitting on the table, and I need to mix up a solution. This is just dextrose, so that is just sugar, and this is a complex reagent. This reaction is actually used to test for aldehydes in organic chemistry. And I'm going to need things to put this into in just a few seconds. There we go. Now it's working. 4. So what we have going on is a spontaneous reaction, a voltaic cell. The dextrose ends up reducing the stuff that's in there. Oh, would you look at that? Used it up faster than I expected to be. Anyway, it ended up getting used up quicker, reacting faster than I thought. Well, I'll go grab the other bottle, and you'll be able to see the significant difference in the two. This is the new bottle. This is what it used to look like. What we've done is that there were silver ions present, and that silver has literally mirrored the inside of the flask. So this entire inside of this has been coated with a nice layer of silver. It is literally, if you were here, I'd pass it around through the class, and you'd be able to see yourself in the mirror. This flask as well, if I can get a waste container, has actually had the same thing done to it. It is now nice and silvery, whereas another one is completely clear and transparent. So the reaction that we're looking at is the reduction, spontaneous reduction of silver. And ladies and gentlemen, that's it for today. I hope you had a good class, and I will see you on, oh yeah, gloves are green, so they somewhat are transparent in some cases. So gloves are green. I'll see you next day. I'll see you on Monday, and we'll finish all this material off. Take care.